Hello everyone, my name is Mattia Cersullo and I'm a student from University of Calabria. Today I'm presenting our paper on detection strategy for setpoint attack against differential-drive robots. This work was made in collaboration with Concord University, and the co-author of this paper are PhD student Cristian Tiriolo from Concord University, Professor Giuseppe Franz from University of Calabria, and Professor Lucia from Concord University. First, I will do a brief introduction about well-mobiled robots. Then I will talk about our problem formulation about setpoint attack detection in well-mobiled robots. Then I will present to you our proposed solution and our results. There are a lot of potential applications of well-mobiled robots that goes from surveillance, military application, agriculture, and disinfection. In many applications, well-mobiled robots are remotely maneuvered from a control center that send the setpoint signal to the robot. In this type of networked framework, one of the problems is the one about cyber attack. The well-mobiled robot controller receives a desired value, discrete time reference setpoint value, from the control center. This value is sent via an unsafe communication channel. So the attacker is able to corrupt the transmission signal, causing a loss of the tracking capabilities. So our objective is to design an anomaly detector that is capable of discovering setpoint attack against reference value. One of the main difficulties is that the reference value is not a function of the closed loop evolution of the system, and its evolution is unknown to the tracking controller. And also, existing anomaly detectors are ineffective in this type of scenario. Our main focus was on differential-drive robot. Here I'm presenting to you the differential-drive robot kinematic model, where R represents the radius of the wheel, and D represents the axis length of the wheel. Omega R and omega L are the angular velocity of the right and left wheel, and theta is the orientation of the robot. The robot is also subjected to wheel's angular velocity saturation constraint that are shaped like a box, and where here omega bar represents the maximum angular velocity that the wheel can reach. By using a linear input transformation, the differential-drive kinematic model can be recast into an equivalent unicycle model. Here we have V and omega that represent the linear angular velocity of the robot. Also, V and omega are subjected to a rhombus-like constraint. By resorting to this change of coordinates and applying the dynamic input transformation, we can the unicycle model is equivalent to a two-single integrator model. Here, Ts represents the sampling time that is used to discretize the model. The feedback linearized vehicle model also is subjected to rhombus-like input constraint, but in this case, they are dependent on the orientation of the robot. But it's possible to find a not-empty worst-case inner approximation, as we can see in the figure, that does not depend on the orientation of the robot. Now I'm presenting our proposed control architecture. We have a two-loop controller for constraint reference tracking. We have a state feedback primer controller and a command governor for worst-case input constraint enforcement. Also, our detection module, leveraging on two twin command governors CG1 and CG2, and two pseudo-random vector PRV-E encoder and PRV-D decoder. By considering the constraint feedback linearized model, we can design a state feedback controller to ensure the reference tracking. Here, RB represents the setpoint signal that is translated into the linear system frame. Now I will do a brief introduction on the command governor. The command governor is a nonlinear device that filters the reference signal RK that is given to the primer control. And the command governor objective is to ensure that the robot's worst-case input constraints are satisfied. At each time k, the command governor computes the best feasible approximation GDK of the reference value. Here, V represents the set of feasible commands that is constantly applied, that if constantly applied do not lead to any constraint violation. Now I'm presenting to you our set point detection strategy that consists in two twin command governors modules that are added on the control center and on the robot sides. In absence of attack, we have that the output of the two command governors are equal. This is due to the fact that the command governor performs the best feasible approximation of the reference value. So by giving as an input to the second command governor the best feasible approximation, the output will be equal to the input. So as a consequence, we can an anomaly is presented if the output is different from the input. So our detection strategy consists in calculate the difference between these two signals, and if the difference is measured of a small threshold, the anomaly is detected. But if the attacker has a full knowledge of the system dynamics and sufficient disclosure in disruptive resources, he can perform a stealthy setpoint attack by emulating the CG action. So here, G1A is the best feasible approximation of the desired attacker trajectory. But this type of attack can be prevented by randomizing the transmitted reference signal via a PRV encoder and decoder modules. Here we have the Hadamard multiplication for the encoder and Hadamard division for the decoder. Now I'm presenting our simulations. This is our configuration because the proposed detection strategy has been tested by considering a differential-drive robot with these parameters, where B is the feedback linearization parameter, and omega, the maximum angular velocity, has been set to 10 radius per second. The robot is required to track a predefined H-shape reference trajectory, and this is the tracking controller with the feedback linearization that we used. Also, we suppose that the attacker has full knowledge of the robot model, of the primary controller, of the CG, and of the detector. So the attacker is capable of eavesdropping the data transmitted on all channels and corrupt the transmitted set point. The objective of the attacker is to force the vehicle to track a different reference signal. And so the attacker will compute the best feasible approximation of this reference signal and avoid to be detected by our detector. Also, if an attack is detected, the robot will stop in the current position. In the first simulation, we suppose not to have our PRV logic. So we can see here that when the attack is performed, the detector is not triggered. This is because the attacker is performing the best feasible approximation of the attacker reference value. So we can see how the attacker is capable of ejecting the vehicle and bypassing the detector. And it can do this by also avoid to violate the constraint. We can also see that after the attack is finished, the robot is capable of following the predefined trajectory. Then we decide to simulate the same scenario with the PRV logic. But here we can see that when the attack is performed, the detector is triggered and the robot stops in this current position. We can also see that all the constraints are satisfied, and that when the attack finishes, the robot is capable of following the predefined reference trajectory. So in conclusion, an anomaly detector for setpoint attack against remotely maneuvered differential-drive robot has been presented. This solution is an extension of a recent detection scheme that was originally developed for linear system. Here we deal with a nonlinear dynamics of ground autonomous vehicle, and we achieve that by using a feedback linearization and worst case characterization of robot constraint. Also, we by simulation result will testify the benefits of this proposed solution, and future studies will be devoted to implement this detection architecture on commercial autonomous vehicles. Thank you for your attention.